We've all been there, right? Standing on a beach, watching the ocean creep up the sand and then, hours later, retreat back out. It's this incredibly reliable rhythm. But what if I told you that daily ebb and flow is way more than just water? It's actually the pulse of the cosmos, a silent force that shapes entire worlds. Today we're going to dive in and figure out exactly how it all works. And look, that is not an exaggeration. The very same force that pulls water across a shoreline is powerful enough to spark volcanoes on distant moons and, yes, even stretch you into spaghetti if you get too close to a black hole. It's one of the most fundamental and frankly coolest forces in the entire universe.
So what is this universal force? Well, it all starts with something we all know, gravity. But here's the key twist. It's not just gravity's pull that creates tides. It's about how that pull changes over a distance.
And that right there is the most important thing to get. A tidal force isn't a simple tug, it's a stretch. Just imagine gravity pulling a little harder on the side of an object closer to it and a little weaker on the side that's farther away. That difference, that differential pull, is the tidal force, and it's subtly warping and stretching everything it touches.
Okay, so let's bring this down to Earth. For us, the main source of that stretching force is our celestial next-door neighbor, the Moon. So let's zoom in on this dance between the Earth and Moon to see how it creates the tides we experience every day.
Now, you might be thinking, wait a minute, isn't the Sun way more massive? Shouldn't it be in charge? And normally you'd be right, but remember, tides are all about the change in gravity with distance. And because the Moon is so much closer to us, its tidal force on Earth is actually more than double the Sun's. It's a huge difference.
You can see the effect perfectly here. The Moon's gravity tugs hardest on the side of the Earth closest to it, and that pulls the ocean water into a bulge. But what's truly amazing is that it's not just the water. The entire planet, all 13,000 kilometers of it, gets stretched into a very slight football shape.
Get this, the solid ground you're on right now is being stretched. That means twice a day, whether you're sitting at your desk or lying in bed, you are physically rising and falling by about 30 centimeters, or about a foot. You just don't notice it because, well, the entire continent is moving right along with you. Okay, so a bulge of water on the side of Earth facing the Moon? That makes total sense. But hang on, that doesn't explain why most places on the coast get two high tides every day. Where in the world does that second bulge on the complete opposite side of the planet come from?
This is the part that feels a little counterintuitive, a real head-scratcher. But the answer is actually incredibly elegant. It all comes down to realizing that the Earth and Moon are moving through space together in a very specific way.
Let's walk through this, because it's pretty neat. First, the Moon doesn't just orbit the Earth, they both orbit a shared center of mass, a point called the barycenter. So as the Moon pulls the ocean on the near side toward it, it's also pulling the entire solid Earth away from the water on the far side. That water on the far side kind of gets left behind, creating the second bulge. It's just like being on a fast-spinning carousel and feeling your hair fly out away from the center.
And boom, there you have it. The Earth just spins on its axis once a day, carrying you and me in every spot on the globe right through both of these watery bulges. And the result? 2 high tides and 2 low tides every single day. Mystery solved.
But of course, the Moon isn't the only player in this game. The Sun is out there too. Its tidal force is weaker, sure, but it's still significant. You can think of it as a kind of cosmic amplifier, or sometimes a dampener, depending on how it lines up with the Earth and Moon.
So when the Sun, Earth, and Moon are all in a straight line, which happens during a new moon and a full moon, their tidal forces team up. They combine to create those extra high tides and extra low tides we call spring tides. But when they form a right angle, like during a quarter moon, the Sun's gravity actually pulls against the Moon's. They sort of cancel each other out, giving us much weaker, less extreme tides known as neap tides.
And you know, this gravitational stretching doesn't just slosh water around. Over billions of years, it has profoundly reshaped our planet and actually our entire celestial neighborhood. The effects are huge.
It kicks off this incredible cosmic exchange of energy. Think about it. As the Earth spins, those tidal bulges drag against the planet, creating friction. This acts like a giant brake, slowly, ever so slowly, making our days longer. But that energy doesn't just disappear. It gets transferred to the Moon, which gives it a little boost, pushing it into a higher orbit, a little bit farther away from us year after year.
And how fast is it moving away? Well, believe it or not, it's about the same speed your fingernails grow, just a few centimeters a year. But over billions of years, that really adds up. The same force that gives us high tide is slowly pushing our moon away, which means billions of years ago, our days were way shorter and the moon looked huge in the sky.
So what happens when this process plays out for long enough? You get something called tidal locking. This is exactly what happened to our moon ages ago. The Earth's powerful tidal forces slowed the moon's spin until one rotation took the exact same amount of time as one orbit. And that is the reason we only ever see one side of it, the man in the moon, from here on Earth.
And this isn't just an Earth-Moon thing, it happens all over the cosmos. Jupiter's insane tidal forces constantly knead its moon, Io, generating so much internal heat that it's the most volcanically active body in the whole solar system. For Saturn's moon Enceladus, that same tidal heating probably keeps a liquid ocean hidden beneath its icy shell. And near a black hole, well, the tidal force gets so strong it will literally stretch you into a string of atoms. Astronomers have a great name for it: spaghettification.
So, the next time you see the tide roll in, just take a second and remember what you're really watching. It's not just water moving. You're seeing a universal force at work, one that sculpts planets, might create the conditions for life in the craziest places, and governs the grand cosmic dance of the universe. It really makes you wonder, doesn't it? What other incredible secrets does this force hold on worlds we haven't even discovered yet?